This video is an overview of performance on the first midterm exam and how it was scored. Stepping through the different questions, a key thing within the first one is to recognize that it was involving ammonia as a solvent. Wasn't discussing what happens when we put ammonia in water, but when ammonia would be the solvent in question. Here's some student work describing the corresponding chemistry, how we can have both an acid and a base form as we have the ammonia gain and lose a proton, and that we could then look at that as the analogous treatment for the Kw of water. Within this one, we're looking at information about the pH of water and whether that gave us insights as to whether it was an endothermic or exothermic process. Most responses began, first of all, describing in a good way what was the relationship between pH and the hydronium concentration. So what did that mean in terms of the reaction shifting towards or away from the products? The resulting then discussion led to the thought that the K value here was different. It had a temperature dependence. It led to an endothermic description. The analysis on whether it was endothermic or exothermic, students did different things. This is an example of looking at the corresponding change in the K values and looking to see whether that meant it was an endothermic or exothermic reaction, but different reasoning could also be used in that section. Calculation involving a solution for the sodium fluoride with a pKa value listed for HF. Within this one, the student begins by recognizing that we have a strong electrolyte for this ionic compound. It's going to dissociate completely. So let's account for that first. The sodium is not going to be, cation is not going to be influencing the pH, but our conjugate will. So let's put that then within a equilibrium expression where we have an isotable where it's acting as a weak base, producing the hydroxide. To set this up then, we need a K value for this. So if we take a pKa value for HF, we have to somehow get it to be the Kb for the corresponding expression that we have here. Students did different things within that. You could convert the pKa to a Ka and then use Kw. You could use a relationship that we see here. But however you go about it, we need to get a Kb for the corresponding equilibrium expression that matches the isotable. When we work through and solve for that, we're solving for hydroxide, and then we can check if our assumption of neglecting X could be neglected, and it could be. This one here, we had quite a few different responses. The scenario beginning with a container in which calcium carbonate had decomposed and then partially decomposed and included then in equilibrium calcium carbonate, calcium oxide, and the carbon dioxide, and then changing the system here by pulling a piston outward isothermally and explaining what happens and how is thermodynamics part of the explanation. Let's look at the details within this one. So the idea here, many folks began with saying, okay, if we pull the piston outward, the volume's increasing, pressure's going down. Key thing there is it's going to be changing the pressure for the CO2 and largely leaving the description for the solids unaffected. They're just now in a large container. We have a description for what happens then in terms of how Q and K are no longer the same. A description of if you, one way you could think about the direction would be to think about, well, what is the Q value now and what does that mean as far as does it go in a forward or reverse direction? I like a lot of the details here, but I wasn't seeing necessarily a connection to entropy in this, what I would say, otherwise comprehensive discussion. This next one right here, I like again that it's noting how the gas is being affected and the entropy of the gas is increasing. The entropy for our solids that we have in there, not really changing, but the entropy for the gas is increasing as it's occupying a larger volume. And also this important distinction that when we're looking at the entropy, we don't want to be thinking about the system as a whole, because when we're looking at the entropy change, yes, everything's in the same container, but if we're thinking about a comparison of the reactants and the products, That's what our delta S is in terms of. So I really like the discussion here of thinking about it specifically in terms of a comparison of the products and the reactants. Important detail within this. Now, it goes on to say that the reaction goes towards high entropy. And within this one, within this language, I know there's more details provided, but I wasn't really sure I understand this kind of statement. You know, if we've had it where the gas is now at a higher entropy as the volume's expanded, is this saying that there's an additional change that goes from a high to a higher entropy? Wasn't really clear from the language within this part what the student meant. Some students would point out that gases have a higher entropy and therefore the reaction must proceed forward. But that's also sort of lacking, because if that was the case, why didn't it just go completely towards the gases to begin with? Why did we have initially some calcium carbonate present? And after we expanded, why would we still have calcium carbonate present even at that equilibrium condition? This particular one begins once again describing what happens when the piston's being pulled outward, how we have a change in entropy, and what does it mean to consider the change in entropy for the CO2, and how then the change in entropy of the CO2 can be connected then to the Gibbs free energy. This idea here that a lower Gibbs free energy, so that is our direction. We're going from a higher to a lower Gibbs free energy. Something that has a lower Gibbs free energy is in a sense more stable. We have stabilized the gas here, increasing its entropy by increasing the volume. And the direction of the change, therefore, is toward the gas. When we're thinking about a thermodynamic explanation involving entropy, these are the kind of details that we have here. Key thing within here was considering how the change was leading to different entropy terms, different Gibbs free energy when we're comparing the reactants and the products, because after all, that's what our delta G ends up comparing. A lot of different ideas shared within this section. This next one, we're looking at the composition of a polyprotic acid. Different pKa values are listed. So this first part right here, we need to keep track of the different pKa values and what they correspond to as we donate 1, 2, 3 protons. How we could then talk about a particular species being having the highest concentration using 1/2 of the corresponding pKa values. These kinds of sketches, whether it was looking like the one here on the left or something a little bit more avant-garde with the one on the right, I thought that these were important within the analysis because they are a way to make sense of how different pH values corresponded to different compositions. If we look within this first one, and we are considering Na2HA, that's the HA2 minus, we know what the initial pH value would be. It's going to be basic, as we see within our description right here for our 1/2 of the corresponding pKa values. So if we're adding HCl and making it more acidic, it's going to be shifting and become more protonated. The mole amount of the initial HA2 minus would be going down. This would be a similar treatment here where we're asking about what happens if we take the HA2 minus and we make it even more basic about how we have a shifting then. Within this one, we're looking at how we can have potentially cations and anions contribute to the pH for a salt. As I look at this, we have a strong acid and we have the PO4 3-, which is going to be a pretty good base, so I can easily place these two from the lowest to the highest pH. As I look at the others, I see aluminum 3+, which is going to be an acidic cation. Nitrate's not going to contribute. Within this one, I sort of need some data. Here I show different Ka values for phosphoric acid. This illustrates again that the PO4 3-, really small Ka. So we're going to have the PO4 3- being a pretty good base. Placing this one relative to the aluminum nitrate, having some Ka data would help. So I accepted the placement of those two being switched within your rankings. I thought either was acceptable. If you argued that this was going to be behaving and being a stronger acid than the aluminum 3 plus, I was fine within the analysis, or if you switched it the other way. Description here of a scenario where water is entering a bathtub from a faucet. It's leaving at the bottom, it's entering at the top, and the water level is remaining constant. This was really split. About half the class said, yeah, this was a good example of dynamic equilibrium, and we shouldn't be fooled by this. Macroscopically, seemingly there is no change because there was change taking place, and that they were taking place with opposite rates. So overall, there was no net change. About half the students said that. About half the students said, no, that's not a good example because it's taking place in an open system. We do not have equal and opposite dynamic processes taking place. We have two different processes. We have water leaving at the bottom and water entering at the top. And so if you have a system here that's an open system like this, you can't have dynamic equilibrium. I agree with the second example. It's like the discussion that we had, we saw within Atkins for what happens if you have a burner like this with a flame. You can have the flame appear constant, but this was not a case of dynamic equilibrium because we continually had our gas entering the flame and then being combusted within this. Similar to on our practice test when we were looking at the description for burning of a candle. Within this one, overview of Le Chatelier and how would it be suitable for this particular scenario? Would the shortcut of Le Chatelier be adequate, sufficient to explain what's going on here? Well, if we look within this, key detail here is that it's set up within with a movable piston. So if we add some of the gas that's listed as a reactant, well, Le Chatelier would say if we're increasing the concentration of the reactant, it's going to shift to the right. But it would also say, no, as we add that with a movable piston, the volume is going to increase and all the partial pressures are going to decrease. That would be leading to a shift to the side that has the more gaseous reactants in this case. So in this scenario, we need to know more specific values. We need to be able to compare Q and K. Our shortcut of Le Chatelier is not sufficient because we had two different aspects changing. And within Le Chatelier, if those are in competition, if one suggests one direction, the other suggests the other, it's not going to lead us to an answer. Choice of questions here. Most students chose the first one and discussed the stability of the conjugate within their reasoning. And what did it mean to have the charge delocalized and spread over a larger area with our acetate anion? The second one, some students discussed what a large or small pKa value meant and connected that to Ka values. I thought the stronger responses would also consider a structural description of the conjugate. In some ways, that was another connection to what we would have had with the first part of the question. With the other one could choose from. Here was a discussion of that, of what did it mean to consider the stability of the conjugate or its readiness to reattach a proton within that. Within this, two different questions. Most students chose the calculation. Here's a run through within the calculation. Key step would be to recognize that sulfuric acid is a strong acid in terms of donating the first proton, so we can look at that stoichiometrically. Then put that into our subsequent ice table. So we have a head start on the initial value there. When that one goes through, I set this one up so that it is fine in terms of our 5% rule. The initial acid strength was high enough so that we could easily do the math here, neglect x, that whole term cancels, and with the corresponding x value, we could then use it to figure out what the pH was. This one, students did, overall I was impressed as far as working through the two different parts and coming up with an answer on that one. Here would be a discussion for the second one, looking at the role of the autoprotolysis. This was explained in different ways, but it was really coming down to how was the KW calculation being affected. if we had something that was a strong electrolyte versus one where we had equilibrium conditions present as well. Turning to our last question here, it began by could we write a balanced equation and then take our scenario and look at the equilibrium constant in different ways. So here's some shown work for this one. So first of all, being able to come up with the equation, I see reactant A goes from a value of 10 bar down to 6 bar. That would be a change of 4. And the product B goes from 0 up to 8 to reach equilibrium. So I agree, it seems like for every 1A, it's leading to a change of 2B. A is the reactant going down, product is the B. If we take those values, then we can put in and make a K expression. K was involving bars, so we could simply use those particular values. One mistake I saw occasionally, students would forget to include the squared value there in the numerator, but we need that to match up with our balanced equation. We have a conversion then between K and KC. Most folks did a good job of thinking of what would be the appropriate units for R within that. When we're thinking about what would happen if it was in reverse, not guesswork there, we can just flip over our numerator and denominator, and either do that within our calculation or just take the value and take what we had calculated and take our reciprocal within that. We were good to go. Most folks did a good job recognizing that our Q value is going really small, down to 0 as we were removing one of the things that was in our container, and this was then giving us insight for how we'd reach the subsequent equilibrium. So here's an ice table that was describing that as our B value went down to 0. What did it then mean to be set equal to what our K expression was? The one mistake that I saw oftentimes for someone who was really on a roll getting to this point was right within this point, within the K expression. I like what's going on, but if we return back to what our expression would be for the K itself, we need to have the 2x term, that entire term, squared, because that's what matches up with what our description for the K is. Overall, within this one, though, I was looking, as we got to the bottom, was the K expression correct, and was the ice table correct? Within this whole set, then, so we had 11 questions. The way that this got scored, every question was scored on a 3-point scale. By me, I went through question 1, all the questions at the same time, question 2, all the questions at the same time, all the responses at the same time. And my scoring scale was on a 3-point scale for everyone. If it was a calculation, was the calculation entirely correct? That would get you full credit of 3. If it was an open response, was it an above average open response? Was it an exceptional open response? That would be worth 3 points. 2.5 often meant there was a minor calculation error. 2 I viewed as an average open response. It matched what the class as a whole was doing. And if there was something less than 2, it was involving several mistakes for a calculation, or maybe there were missing ideas. Overall, the response for that question was below what the class average was. So I took all of it, put it into a spreadsheet. So I have everyone's responses coded for each of the different questions. If you're interested in this particular set of data for you, I can share that with you. So the highest score overall then I set to 100%. A score of 66, therefore, would be about 2/3, which would mean, okay, if the very top score, if they were entirely above class average, everything was being correct, a score of 66 would be, okay, you were at the class average. It means overall, you were getting 2s where the very top score was a 3. And the higher scores reflect more above average responses. So if I look at the overall distribution for how scores came out within this test, if you were below 70, if you're closer to this 2/3, it meant that overall you had more average responses and fewer ones that were either entirely correct or above the class average. If you're within this group, that meant more above average responses. If you have questions within the scoring or your own particular responses, I think that the one way that you could do would be to respond within this video, and then we can also meet individually.